This is lesson 4.2 on inverse functions. Now when we talk about a function, we talk about its inverse or its inverse function. What we mean by that is a function and its inverse. Those are two functions that basically undo each other's work. So the definition of the inverse of a function is the function such that the composition of those two functions. Remember a couple sections back, at the end of Unit 2, we talked about the composition of functions, a function inside of a function. When we put the inverse of f inside f, or vice versa, if we put f inside the function, or if we put f inside the inverse of f, they're going to undo each other. So any number that you put in there, f inverse or f inverse of f of whatever, you're just going to go in one big circle. It doesn't change a thing. So inverse functions are pairs of functions that essentially undo each other. Now the reason that we talked about one-to-one functions before talking about inverse functions is because it's only one-to-one functions that actually have inverse functions. And we'll see in just a moment why that's not surprising. Now if we look at the graph of the inverse of a function, if we compare the graph of the original function and the graph of the inverse, what we will notice is that for each point on the original function, the x and the y values swap places. So if we had the point 3, 2 on the original function, we're going to now have the point 2, 3 on the inverse. The x's and the y's switch places for every single point on the graph. So that gives us a little bit of insight as to why a function must be one-to-one in order for it to have an inverse. Because if it weren't one-to-one, so in other words, if we had two different x values with the same y value, that would make it fail the horizontal line test, so therefore it would not be one-to-one. Once we swapped the x and the y values everywhere, that would mean in the inverse, we'd have one x value with two different y values, thus making it not a function. So we will only talk about inverses when we're dealing with one-to-one functions. Another nice property of inverses is that the inverse function of an inverse is just the original function. So we're kind of, again, going in one big circle. Now what this means, therefore, is that inverse functions, or the inverses of a function, the inverse of a function will also be a one-to-one function. So that's going to be important to remember for our application problem that we're going to see. For the drill problems, we're going to use this first fact that we've written here, that the x and the y values swap places. So the way that we're going to find the inverse function given an original function is to swap the x and the y places and then resolve for y. We'll see that in a moment. Now the second fact, that the inverse must itself be a one-to-one function, we're going to need to be mindful of that with our application problem. We're still going to be finding the inverse of some given function, but at the end there's going to be one additional step that we have to take to ensure that we are in fact working with a one-to-one function as our inverse. Alright, let's start up with an easy one. So we're asked to find the inverse function of f of x equals 3x minus 7. Now remember that only one-to-one functions are going to have inverse functions. We don't need to check whether or not this is one-to-one for the purposes of our drill problems. I will only give you functions that are in fact one-to-one. But be mindful that in general, that's something that we need to check for. But for the problems that we will see, we can assume that this is one-to-one and just get down to business. Okay, the very first thing that we're going to do, we said that the inverse function essentially swaps the roles of x and y. Well, that's all well and good, but where is y here? We don't see a single y at all. Remember, y is usually what plays the role of the function itself, f of x. So the very first thing that we need to do here is go ahead and just rewrite this as y equals the function that we were told. So y equals 3x minus 7. That's the very first thing that we need to do. Okay, now that we have our x's and our y's, we're now going to swap them. So everywhere you see a y, write x instead. Everywhere you see an x, write y instead. So we've swapped the roles of x and y. Now we want to solve for y again. So in this case, this is just a nice linear equation. We know how to solve for things. So let's get the y completely by itself. So let's add 7 to both sides. So x plus 7 equals 3y. And then I'm going to divide both sides by 3. So I have x plus 7 all over 3 equals y. And I'm done. This is my inverse. So the inverse function is going to be this right here, x plus 7 over 3. Now, just for the sake of demonstration, let me do this in a different color just to emphasize. This is extra. You do not need to do this for the problem, but I want to show you that, remember we said that kind of the definition of the inverse is that this is true. F inverse of f of x is just x, or the other way around works as well. Let's check just one direction. Let's show that f inverse of f of x equals x, so the composition of these two functions. So if you recall, what the composition means is that I'm going to take this outside function, so f inverse in this case, everywhere I see my variable, I'm going to replace it with an exact copy of what's inside. So in this case, f of x. So f inverse of f of x. So f inverse is this right here, but instead of x, I'm going to have f of x. So f of x plus 7 over 3. This is f inverse of f of x, this right here. But I know what f of x is. It's 3x minus 7. So let me go ahead and write that in. 3x minus 7 plus 7 over 3. Well, negative 7 plus 7, those cancel, so I'm left with 3x over 3. And sure enough, that's just x. So this is true in this case. F inverse of f of x is just x. You can take time to check it out for yourself, but if we switch it around, we're going to get the exact same thing back. If you recall when we talked about composition of functions earlier, this isn't always true. When you change the order of composition of two functions, in general, you don't get the same thing back. For inverses, however, you do. F inverse of f of x is just x, and f of f inverse of x is just x. Both orders will always give you x back. So once again, what we've done in blue here, you do not need to do this for the drill. We're most likely not going to have an application problem where you need to do this. I just wanted to demonstrate that what we said before does in fact work. When we do this for any function and its inverse, we will always get just x back. This demonstrates that the two functions undo each other. That was so much fun, let's do it again. So find the inverse function of f of x equals 2x plus 3 over 4x minus 1. So we have a more complicated function this time. We're dealing with a rational function, but notice here that the numerator and denominator are both linear. So it's more complicated, but it's not going to be too terribly difficult. The process is the exact same. We're going to first write in our y, so we're going to rewrite this as y equals 2x plus 3 over 4x minus 1. Then we're going to flip-flop. We're going to switch the roles of x and y. So now I have x equals 2y plus 3 over 4y minus 1. And now I want to solve for y. So I need to multiply both sides here by my denominator, or equivalently you can think of it as we're cross-multiplying here. So that gives me x times 4y minus 1 equals 2y plus 3. So I'm going to go ahead and multiply this out. 4xy minus x equals 2y plus 3. Okay, so I want to solve for y. So I need to get everything with a y in it on one side of the equation and everything else on the other side. So I'm going to add x to both sides and subtract 2y from both sides. So this becomes 4xy minus 2y minus x. I add x, so it cancels on the left-hand side. 2y minus 2y goes away, and I have 3 plus x. So I moved my 2y to the left-hand side, moved my x to the right-hand side. So here I am. Notice that this is very good. I have my y's on the left-hand side and everything without a y on the right-hand side. When we are working on this, we should be able to factor out this y term. So I'm going to factor out this y. So this is y times 4x minus 2. My right-hand side just kind of sits there. I don't really need to do anything more with it. So I have my y here, y times something. I want to get the y completely by itself, so I'm going to divide by the thing that I'm multiplying it by. So when I do that, I wind up with y equals 3 plus x divided by 4x minus 2. And I'm done. That's my inverse function. F inverse in this case is 3 plus x over 4x minus 2. So this takes a little bit of time, but there's nothing too terribly difficult here. This is the hardest type of problem that we will run into for the drill. We might get lucky and see some linear problems. We might see some slightly simpler rational functions like this, but this is the absolute most difficult type of function that we will see on the drill where we're asked to find the inverse of this. We will always follow the same process. Write it as y equals the function, switch the x and the y's, and then solve for y again. It's nothing too terrible. It's basically just our simple algebraic ideas that we used back when we were solving linear equations way back at the beginning of the class. So nothing new here. We're just using old tools in a new way. So here's one that's just a little bit different. It doesn't look all that different, but we're going to see in a moment that this actually requires a little bit more thought than the previous examples did. So find the inverse function of f of x equals square root of 2x minus 1 plus 3. So once again, whenever I ask you to find the inverse of a function, I will always give you a one-to-one function. In general, outside of this class, that's something that we would need to double check. We need to double check that this is in fact a one-to-one function, but it always will be for any problem that I give you. So what we're going to do is proceed in the exact same way. The problem looks almost exactly the same as our drill problems up until the very end. We're going to see a little bit of a difference at the end of our problem. Okay, so I start off by writing y equals the function, and now I change places. My y's become x's, my x's become y's. And then from here, I just proceed as normal. I want to solve for y, so it's trapped inside a square root, so let me get this square root by itself. So let me subtract 3 from both sides. So x minus 3 equals square root of 2y minus 1. And so now let's square both sides. So when I square both sides of this equation, this becomes, I'm just going to leave it as x minus 3 squared. So x minus 3 squared equals 2y minus 1. I want to get y by itself, so let me add 1 to both sides. X minus 3 squared plus 1 equals 2y. And then let me divide everything by 1/2. So I have x minus 3 squared plus 1 all over 2 equals y. And so it seems that we're done. We've gone through the exact same process that we did in the previous problems. We've solved for y. This seems like a perfectly ordinary looking function, so what's the big deal? Let's call this f inverse and go home. Well, there is a problem here. X minus 3 squared. I hope that we recognize that. We know that a quadratic polynomial like this, that's going to give us a parabola. So remember, our parabolas are going to look like this. So let's see, let's just guesstimate. It's going to look something maybe like this. Not the exact graph, but just the general idea. Does anything seem a little bit unusual about this? So we said that that our original function must be one-to-one. Therefore, our inverse function must be one-to-one as well. That's not a one-to-one function. So something is up here. Something's not quite right. What we've defined here is, in fact, not a one-to-one function. So what we need to do, we need to figure out a way to restrict our domain. We need to specify what x values we're working with so that this is, in fact, a one-to-one function. And here's the important point right here. We know that x is going to equal square root of 2y minus 1 plus 3. So notice, x, we know that the square root, what's the smallest that can be? The smallest that a square root can be is 0, and then we're going to add 3 to that. So based on our very first line right here, we know that the smallest value that x can be is 3. In fact, it can equal 3. When our square root equals 0, x will equal 3. But then as y, for different y values, this is going to become a positive number, so it'll be bigger than 3. We'll add that to 3 and get x to be a value bigger than 3. So what we need to do here is we need to specify that x is bigger than or equal to 3. Notice that on our graph, that corresponds to taking only the right half of our graph. Notice if we only take the right half of this parabola, that's now a one-to-one function. If this left part is gone and we only focus on the right part, any horizontal line that we draw through that parabola is going to cross it once. So now we're in good shape. Once we specify this restriction, we're home free. So our final answer in this case is going to be f inverse equals the function that we found, so x minus 3 squared plus 1 all over 2. But don't forget to mention this. This is very important. This is kind of the main thing here. Remember to mention this. So our final answer is not only f inverse equals this mess here, but we have to specify that x is bigger than or equal to 3. The reason we have to specify that is because the inverse function must also be a one-to-one function. If we do not specify this domain here, this is not a one-to-one function. So when we restrict ourselves to x values bigger than or equal to 3, then suddenly this becomes a one-to-one function and life is good again. So for these problems, when we run into these on our application, we're going to follow it the exact same way that we do for our drill problems, but don't miss the twist ending. We're always going to have this funky little thing that we have to look out for. We're going to need to work with our domain so that what we're working with is going to be a one-to-one function.